Welcome back. In this lecture, we will talk about applications of reinforcement learning. Here's our lesson objective. First application is about playing games. Now, games might seem a little trivial, but the nice thing about games, things like the Atari games or Go, or even simple games like tic-tac-toe, they've been very important in advancing the field because the state space is easily understandable. It's very easy to simulate the games in the computer, so to have an agent take actions and get feedback by sampling the state space, it works well. And so as a relatively recent example of this, you have AlphaGo 0, which is an improvement on DeepMind's AlphaGo. In this case, the agent only has some very basic rules about the game, no pre-bootstrap training for the game Go. And even with this, it was able to outperform earlier versions of the Go playing AlphaGo algorithm. Also, they compared it here to supervised learning. And you could see using this rating that's standard for that game, you see how AlphaGo had, took a lot of training time to get up to par with the supervised approach and then reach the previous levels of AlphaGo. But then with more training time, it was able to exceed both of these competitors. Getting to something a little more real world is looking at robotics. And robotics is probably a very clear-cut case for reinforcement learning. The robots are working in a real-world environment where it's very difficult to enumerate the states, but they can provide feedback and they can learn. Also, robots, they can not only provide feedback to the training process by their successes or failures in real life, they're also easy to simulate because they work based on standard physical properties. In this example that's referenced on the slide, they used deep reinforcement learning using deep Q learning, which was invented based on the Atari gameplays, to better grasp objects. And they showed that this could achieve a 96% success rate, even in cases where the robot was exposed to an object that did not appear in the training data. So news recommendation is another interesting case here. In this case, reinforcement learning was applied in an online fashion based on the user behavior. This also used deep Q learning. And so what's interesting about this is there is sort of this bootstrapping part that's offline that is used to train the initial model. And then when it's online, the model provides results, and based on the user's feedback, so the user's telling the model through the user interface, hey, this is useful, this is not, the model then makes updates, either minor updates or major updates, which is running a mini batch of gradient descent and takes a longer time. So here what you have going on is in the online method, you have ongoing training of the model occurring in real time, responding to the user's feedback. So as the user is essentially changing the reward function based on their preferences and things that they find interesting, the reinforcement learning model is adapting to it. And another very clear candidate for reinforcement learning that we've mentioned already is autonomous driving. So clearly when an autonomous vehicle is encountering an infinitely large state space, and so the only way to deal with this is somehow sampling that state space, identifying the features within it, and using machine learning. So of course deep learning is heavily used here, but there are many key gaps, including things like how do you validate that it's taking the proper action? How do you ensure safety requirements are met? And there's also something called the simulation gap, where unlike something like a game playing reinforcement learning approach, where it's very easy to simulate a game or even a robot that has somewhat limited things it could do. When you're dealing with autonomous vehicles that could encounter a whole wide range of scenarios, geographies, weather conditions, simulation is much more difficult. And so there's a lot of active area in research on how to improve the simulations and do what's called closing the simulation gap. So anyway, this concludes our lecture on applications of deep reinforcement learning. Stay tuned for more content.